In this next topic, we are going to study about force due to a continuous charge distribution. Force due to a continuous charge distribution. Let me show you first what is the meaning of continuous charge distribution or uniform charge distribution. Suppose we have a curve or a line, and this curve or a line or a length is found to have charges on it such that the charges are uniformly distributed. The meaning of uniform distribution here is that if I look at 1 centimeter of this length and we see a charge of 1 coulombs, in the next centimeter also we see a charge of 1 coulombs, and in the next centimeter also we see a charge of 1 coulombs. Then I can say that every length of this curve has equal amount of charge, and this is what we will call as uniform charge distribution. On the other hand, if we have charges unequally distributed, suppose this portion of the length has 2 coulombs of charge distributed in 1 meters or centimeters, and this portion of the length has 1 centimeter and the amount of charge is 1 coulombs, then this distribution we have to call it non-uniform distribution. This distribution that I have discussed just now, we call it linear charge distribution because the distribution was taking place over a line. The other type of distribution we can talk about is that suppose we have an area, and on this area we are placing charges uniformly, then this distribution we will call it now surface charge distribution. Here again we'll call it uniform if every area that we talk about here, every, let's say, 1 unit area, 1 meter square, 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 and if every area that we have taken of 1 meter square has equal amount of charge, then we will again call it uniform charge distribution, and we'll call it surface charge distribution. Here you can look at another example where we have a sphere and we have charges distributed on the surface of this sphere, not inside but only on the surface. Again, this case also we have to call it the distribution is surface charge distribution. Then if you take a cube, put the charges on the surface, only on the faces, then again we have to call it surface charge distribution. Note, there is no charge right now inside the cube. Again, you can take a cylinder, put charges only on the surface of the cylinder uniformly, and the distribution will be called surface charge distribution. The third type of distribution that we can talk about is that instead of having the charges on the surface of a 3-dimensional body, suppose we have charges inside the body, that means throughout the volume, then this kind of distribution we have to start calling it volume charge distribution. Here you can see in the cube we have charges here in the surface, but now we have inside the volume. Here in the cylinder we put the charges inside the volume of the cylinder, and again this distribution now we will call it volume charge distribution. And of course in the sphere, instead of putting the charges on the surface, if we have the charges inside the sphere distributed uniformly over the volume of the sphere, then we have to call it volume charge distribution. So we have learned just now we have 3 types of distribution of charge: linear, surface and volume. And we will not talk about non-uniform distribution, we will only talk about uniform distribution of charges. Now with each of the distribution we have 3 important properties which we call as lambda, sigma and rho. This lambda stands for linear charge density, the sigma stands for surface charge density, and the rho stands for volume charge density. Now these terms that I have talked just now are very important for each of their distribution. To tell you what does it mean, let me show you this example. Suppose case A, we have a rod where the charges are distributed throughout the length of this rod. Then the type of distribution we have to call it as linear charge distribution. If I tell you that the length of the rod is 3 meters and the total charge present in this rod is plus 6 coulombs, then we define our lambda, which I have called as linear charge density, as the amount of charge present in this length per unit. That means I am going to divide the 6 coulombs of charge present in this rod by the length of this rod, and when I do that I am going to get 6 by 3, which is 2, so we get 2 coulombs per meter. This is what is known as density in this example. It simply means that every meter of the length of this rod has a charge of 2 coulombs. If I compare with the second case, which is your B, we have not the same amount of charge, but we have 12 coulombs of charge. and I can tell you that the crowdedness of the charge is much more compared to the first case. It is still the 3 meter length, but now the charge is 12 coulombs. So if I calculate the density now, which is a lambda 2, I'm going to get 12 coulombs of charge present in 3 meters. When I divide, I'm going to get 4 coulombs of charge present in every 1 meter. That means if I take every 1 meter of this rod, there must be 4 coulombs of charge present in this rod. Clearly, I can say the lambda 2 I have shown you is greater than your lambda 1. It means the density in the second case is more than the density in the first case. So you can understand by now, all density does is that it tells us the value or the amount of charge present in every meter of the length. And it also tells us the crowdedness of the charges. If the density is large, it means the charges are crowded more in that length. Let's take up this example to see how lambda is going to be handy for us or useful for us. Here suppose we have a length of 10 meters, charges are distributed uniformly, but we do not know how much total charge is present in this length. But if I come and tell you the lambda value for this distribution, that means I'm telling you how much charge is present in every 1 meters. And obviously, if there are 5 coulombs present in every 1 meter of this length, in 10 meters there must be a charge of 50 coulombs. We're simply multiplying the lambda value with the total length. You can see from here, lambda was defined as charge per unit length. If I'm going to find the value of the charge, I must simply multiply lambda into L. I'll repeat again. This distribution is linear charge distribution with a value of lambda equal to 5 coulombs per meter. The total length of this rod was 10 meters. Therefore, the total charge present here must be 50 coulombs. And how do we get that? We simply multiply the lambda value into L value. It simply means that amount of charge present in 1 meter length is lambda. Amount of charge present in 2 meter length, I have to call it twice lambda. Amount of charge present in 3 meter length will be thrice lambda. And of course, amount of charge present in L meters length will be L lambda or lambda L. So just remember this, it's going to be useful for us. So just now you have learned or seen, if we have a linear charge distribution, we have a density called linear charge density. It is defined as the amount of charge present per unit length. That is your Q by L. Here I have written dq by dl, that's okay. The unit of this lambda will be coulombs per meter. From this we can anytime write dq equal to lambda times dl. Let me read it out. What does it mean? dq is the small amount of charge present in a length dl where the density of the charge is lambda. I'll repeat again. dq represents the small amount of charge present in a very small length called dl where the density of the charges is lambda. Note, lambda may not be small, but the charge present in a small length will be small. So we have not written d lambda. Please do not write d lambda. Then we can also have surface charge distribution where we have an area. Suppose we have in this case a charge of 12 coulombs distributed over a total area of 3 meters square. When I calculate the ratio of the charge present in this area, I am going to get 12 coulombs of charge present in 3 meters square of area. When I divide this, I am going to get plus 4 coulombs per meter square. This number represents the amount of charge present in every 1 meter square of area, and we call it surface charge density. Clearly you can see the units will be coulombs per meter square. In the first case we have got 4 coulombs per meter square. In the second case we still have the area of 3 meters square, but this time let's say we have much more crowdedness of the charges, let's say 30 coulombs. So when I calculate the sigma now for this case, I'm going to get 30 coulombs of charge present in 3 meters square of area, which means there are 10 coulombs of charges present in every 1 meter square of area. Clearly sigma 2 is greater than your sigma 1, and I can say that sigma value tells us about the crowdedness of charges in a given distribution. So again we can write sigma equals to the amount of charge present in a given area, and I can use this formula in this way, writing Q equals to sigma into A. It simply means charge present in 1 unit area is sigma, charge present in 2 unit area is twice sigma, charge present in A units of area will be A sigma or sigma A. That means if you know the area and if you know the sigma value, then I can find the total charge present in that area. The same idea goes for your volume charge distribution also, where we are going to write rho as the volume charge density defined as the amount of charge present in any given volume. Example, I can have 5 coulombs of charge plus distributed over a volume of 1 meter cube. So this is the density you can see, and again from here I can write Q equals to rho into V. Amount of charge present in one volume is rho, amount of charge present in 2 volumes will be twice rho, amount of charge present in V volumes will be V rho or rho V. The units you can see for rho will be coulombs per meter cube. All these terms that we have discussed just now, they are scalar quantities, and you have to put a plus or a minus in front of this lambda because it will represent a distribution of negative charges or maybe let's say positive charges. Let's go to our main topic, force due to continuous charge distribution. Let me tell you why do we need to have this topic. First of all, we have already seen how do we calculate the force between 2 point charges. Now if you look at this topic, the topic clearly says we are not going to find the force between 2 point charges, but rather we will find the force between a distribution of charge over a length or a surface or a volume and find the force on this charge. So clearly we cannot use Coulomb's law because Coulomb's law is applicable only for your point charges. So I'll repeat again, we are trying to find the force between charges, but this time not between point charges, but this time between the distribution of charges here and between this point charge. In order to do that, let's say we have a curve with charges being present or distributed uniformly on this curve with a density, let's say lambda. I'm saying that we know the density of this distribution. That means how much charge is present in every meter of it, we know it. Let's take up a very small portion of this length and let's call it AB. The length AB here is denoted by length DL. Now why we have done is that because this small elemental length that we have taken can be treated like a point for us, because as I told you, the DL that we have taken is very, very small. So small that we can treat it like a point. So now the charge present here in this elemental length of DL can be taken as a point charge. To calculate the charge present in this length DL, we simply multiply the lambda and DL. So what I can say now is that charge present here and the charge present here are going to apply force on each other. To write that, I'm using the Coulomb's law, which is dF, a vector directed in this direction along your r vector, and r simply represents here right now the distance or the vector pointing from the elemental length towards the charge. To write the force, I have written 1 by 4 pi epsilon naught. I have written the charge here, which is your dq. I have written the charge here, which is your q naught, and I have divided simply by the distance between the charges, square it. And I have written some direction, which is your r cap, because you can see I have written the vector form right now. Now clearly this is the force between that elemental length and the charge q naught, and this is not the force on the charge q naught due to the whole length of this charge. In order to find the total force acting on this charge due to all the charges present in this length, we are simply going to come and integrate our equation that we have. When I do that, I'm simply going to integrate both sides. Now you can see the right hand side represents the force experienced by the charge q naught, not only by the length dl, but by all the lengths dl, 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 and all the lengths we have taken now. When we integrate this, it simply means that we are trying to find the force on this charge, not only due to the charge present in this elemental length AB, but all the charges present in this length, another length dl, another length dl, another length dl, and all the lengths in this curve. And the charges present in them also will be dq, 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 and dq, and so on. So you can see I have taken the 1 by 4 pi epsilon naught, which is constant when I integrate. The q naught is of course a constant, but we are integrating or adding up all the charges in that entire length, so we have written dq inside the integration. The r that we have is again inside the integration is because it is not a constant. As you can see, the distance between this charge and this length is r, but if I talk about this charge and this charge q naught, the distance will be different and it will not be your r anymore. It will be some other distance. So clearly your r is not a constant and it stays inside the integration. and obviously even the r cap that we have, the direction is going to change. Now you have seen, in place of your dq, what we can do is that we can write lambda into dl, and as I told you, we are talking about a uniform distribution, because of which your lambda is going to be a constant. If it was a non-uniform distribution, this lambda will not be a constant. So here you have, let me read it out to you. What does it mean? It means that if I have a charge distributed over a length and we are to find the force on a given charge placed at certain point, then you must use this formula to find the force on this charge due to the whole distribution of these charges here. Clearly I can say, if the lambda is large, that means if the density of the charges is much more, what you expect is that even the force must be quite large. So you can see the dependence of this force on this lambda. Similarly, if we go to your surface charge distribution, here again we are trying to find the force acted upon this charge by this whole distribution of these charges on a given area. Now obviously we cannot use Coulomb's law because they are not point charges. So we have to take a very small area which we represent by ds, and this area is so small that we can treat it like a simple point. Now I can say this is a point and this is a point, and now we can apply Coulomb's law. Now to find the amount of charge present in this small area ds, we must know the density of charges in this whole surface. Let's denote it by sigma. So again I can tell you, amount of charge present in one area will be sigma, amount of charge present in two area will be twice sigma, amount of charge present in ds area will be sigma ds or ds sigma. So this is what is known as now dq for us, the amount of charge present here. Now we are going to find the force between this dq and this q naught. To do that, again I am writing Coulomb's law, 1 by 4 pi epsilon naught. I have written the charge dq present on the surface in this small space or small area. I have written the other charge, point charge, which is q naught, and I have divided by distance square, and let's say it has certain direction. Now in order to calculate the force due to the whole area, I must take all such areas in this entire surface such that in each of the ds area the charge present is dq. Here also we have dq. In every individual area we have charge called dq. When I integrate, now I am going to get 1 by 4 pi epsilon naught, which is a constant, q naught, constant again, integrate such that I am taking the charges present in the whole area, in the whole surface S. So this part here represents and taking the charges present in whole area. So you can see I have integrated over dq. And of course this r, as I told you earlier, will not be constant, because if I take the dq here, the distance between these two charges will not be r anymore, but it will be some different r. Hence your r and your r cap are not constant. So they stay inside the integration. Now again this dq can be replaced in terms of its density by writing sigma into ds. Again I can say, if your distribution is non-uniform, sigma will not be a constant, but if your distribution is uniform, sigma will be a constant, and hence I can take it out of the integration. So what we have done just now is that I am going to use this formula to find the force on the charge called q naught due to a distribution of charges that we have over a area with a density called sigma. And obviously if the sigma is large, that means we have more crowdedness of the charges in this area, and because of which the force on this charge will be very high. So you can see the force depends on your density sigma. And finally, when we take up this example where we have volume distribution of charges, we have defined density as charge present in a given volume or per unit volume, the units of which is coulombs per meter cube. So suppose we have this case where we have a volume and the density in this volume is rho. We want to find the total force on this charge due to all the charges present in this volume. In order to do that again, to be able to apply Coulomb's law, we are going to treat a very small volume inside this body where the volume is dV and the charge present in this volume will be dq. So I can write the charge present dq will be rho times of dV. Now if I apply Coulomb's law, I'm going to write the force between that small portion of charges and the charge dq is given by this formula here. Again, as you know, we want to find the force experienced by this charge due to the whole volume, because of which I'm simply going to integrate this equation, and I'm going to get 1 by 4 pi epsilon naught q naught as constant, integration of dq for the whole volume V. That means we are going to add up all the charges that are present in the volume V, and then we have r square and then r cap. Again, I can tell you dq can be replaced by sigma into, not sigma this time, you make a change, it's not sigma, it is rho. So I've written a rho here and I must write a rho here. And of course, if it is a uniform distribution, your rho is going to be constant, so it is out of your integration. So you can see again here, if the rho is very large, which represents a very big density or high density of charges, then the force obviously acted upon on that small charge q naught should be very high. Now your job here, now in this topic, your job is just to understand the terms lambda, sigma and rho and see how we are going to use them. You don't need to memorize these equations here. Please do not do that. No need at all. Do not memorize all these steps. Your job was to get an idea of how to apply Coulomb's law when the charges were not point charges. Next, we have a very important topic, which is your electric field. You're going to see we are going to learn something called electric field intensity, another name of which is electric flux density. Let's try to have a basic idea of what is a field. You have here a football field, of course. The rule is the players can kick the football in any way they want, provided the football is within the field. If the football is out of the field, then the players of course are not allowed to kick the football. I can give you another analogy here that is going to be useful for you. So we have here Nihal, and he is in this ring, and we know anybody who enters this ring, Nihal is going to beat him up. If the person is outside the field, Nihal is not allowed to apply force on this person. But if the person is inside this field, you can see what can Nihal do. Similarly, we have seen what Earth can do to us. So this is Earth. Nihal is present at certain point called P near to Earth, and we know Earth is going to apply a force on Nihal, pulling Nihal down to Earth. And we know if Nihal is kept at certain point P, very close, Nihal is going to feel a very strong pull from the Earth. If Nihal is present at a certain point called Q, which is, you can see, a bit far, Nihal is going to experience less pull or less force. And suppose we reach to a very far point R, where Nihal is going to experience a very, very little force. And finally, you can see Nihal has reached so far that Nihal is going to feel no pull from the Earth. I can say when Nihal was at point P, Nihal was inside the field or gravitational field of the Earth. At point Q, again Nihal was still inside the gravitational field of the Earth. Even at point R, Nihal was still inside the gravitational field of the Earth, because at these points Nihal was experiencing gravitational force. To tell you, because mass is something which experiences gravitational force. But you can see this point S is clearly outside the field, and I can say that point such as S is not inside the gravitational field of the Earth. Now if you ask me, I can use another word or another term like your source of the field, and clearly the source of the field in this case is your Earth. So if you look at the same example here, but this time we have not taken any mass, but still I can say point P was such a point where the gravitational field of the Earth was acting or is going to act. That means if I'm going to keep any mass at this point P, that mass must experience gravitational force. Notice I can remove the mass, still say that there is some gravitational pull or field at point P. The same thing I can say is that there's a field at point Q, there's a field at point R, and there's a field at point S. This point P, you have seen the mass was experiencing a very huge force. I can say this point corresponds to a very strong field. Whereas at point Q, I can say the gravitational field is weak, and the gravitational field becomes much weaker at point R, and I can say the gravitational field is 0 at point S. Notice here, I have taken the Earth to be a mass me, and I have not kept any other mass right now here at these points. But still I can say the point P corresponds to a strong field, point Q represents a point of weaker field, and so on. What I mean is that when we talk about this field being strong or weak or very weak, we do not need to keep this mass here. We simply need these points. So from next time onwards, if I am talking about gravitational field, the two questions that you should ask yourself is, who is the source of the field, and at which point are we going to talk about the effect of this field. The same thing happens when we take your electric charge. When I take an electric charge like your plus Q, you will notice that we'll have a predefined region around it, such that if I keep any other charge, let's say Q naught, within this field, this charge Q naught is going to experience some force. But if I keep this charge outside this field, source charge we can call it now, cannot apply any force on this charge. And we have to say that the field we are talking about is the electric field of your charge plus Q. We can say simply that your electric field of a charge is nothing but a region around that charge where the other charges will experience some electrostatic force. Again, you can see I have just drawn an imaginary surface here, or let's say boundary here, and again I have points like your P, Q, R and S, and I have not kept any other charge. Here I can say point P is inside the electric field of this charge, point P is also within the electric field, point R is also within the electric field, point S is outside this field. So if I come and keep a charge here, other charge Q naught, let's say, this charge will experience force of maybe attraction or repulsion. Even if I keep the charge here, you can see is going to experience a force of attraction or repulsion, and even if I keep the charge here, you can say this charge is going to experience force of attraction or repulsion due to this charge. And I can even say the force experienced by the charge at this point P will be greatest compared to the other cases. And of course here at this point S, if I have kept the charge Q naught, then the force on this charge will be 0. Clearly I have to say that this point is outside the field. What you have learned right now is that if I take any charge plus Q or minus Q, we have to start calling it a source charge. The reason is going to create a field, and this charge itself is the source of that field. And I can say within this field there will be points like P, Q and R where the strength of the field will not be same. Some points will correspond to very high strength and some points will correspond to low strength. And we are going to use a term called intensity for that. So if I say at point P the intensity is very high, at point Q the intensity will be low, at point R the intensity will be much less. So when we are talking about electric field, you have to be clear with two things. The first is you have to talk about the source of the field, which is of course your charge. So you have to talk about which charge. Then you have to talk about the point at which we are going to talk about the field, because you see some points will correspond to very high electric field intensity and some points will correspond to low electric field intensity. Now how do we measure this field? To learn that, first let's have this example again. If you are going to measure the gravitational field, you must take Earth and you must take a mass m at a point where you want to calculate the gravitational field. What you must do is that take the mass and release the mass from this point, and of course if there's any gravitational field there, the mass will be attracted towards the Earth. What you simply need to do is that you need to calculate the force experienced by this mass when kept at this point, and the value of that force is going to tell us whether the field is strong or weak at this point P. Now the important thing is that if I am going to find out what is the effect of Earth at this point, or what is the field of Earth at this point, I must keep a mass as you have seen, but that mass should be very, very small, and we will start calling it a test mass. What we cannot do is that To know the gravitational field of Earth at a point like P, we cannot take Sun as a mass or test mass and keep it at point P. Clearly no chance that the Sun is going to fall on Earth. The Earth will start falling on Sun. What I want to say is that you cannot take a test mass to check the gravitational field of the Earth bigger than the mass of the Earth itself, but you have to take a very small test mass. Similarly, if I am going to measure the electric field at these points created by the source charge plus Q, then I must take a charge which I am going to call it as test charge, and the value of that test charge must be very small. So I have written Q0 tends to 0. So I have taken this test charge and kept it point like your P. When I do that, I can say that this test charge is going to experience some force, and when I use the Coulomb's law, I am going to get F equals to 1 by 4 pi epsilon naught, the source charge multiplied by the test charge Q1 Q2, the distance between them, let's say r square, and let's say certain direction. If I tell you right now both are positive, then the direction of force on this charge will be away from the first charge or the source charge. The magnitude of this force is going to give us an idea of how big is the electric field at point P. Similarly, if you are going to find the electric field at point P, we are going to keep this test charge not here, but we'll keep it at point Q. Clearly you can see the distance is increasing, because of which the force is going to decrease. So I will say that the electric field at point Q will be small. Now one thing is very important that you should understand here is that when we are talking about electric field, we said electric field of this source charge, and I said electric field of the source charge at this point. Notice the test charge is simply helping us to find the field. The test charge, that is your Q0, is not creating the field. So obviously this cannot be the measurement for your field, because you can see the test charge is appearing in this formula and it has nothing to do with the field created by the source charge. So some way we have to get rid of this test charge. Now one way to do that is we take our force and we divide by our test charge. You can see when we do that we get 4 pi epsilon naught Q0 by r square, some direction, and we have divided by your Q0. So now your Q0 and this Q0 gets cancelled, and we get F by Q0 equals to 1 by 4 pi epsilon naught. We have the source charge, we have the r square, and we have some direction. Now clearly this is not force, but we have to call it force per unit charge. This force per unit charge, if you look, is clearly the property of the source charge, and it's a function of your distance of the source charge from certain point. This is what we call as electric field at that point. So what is electric field or electric field intensity at a point? So your electric field intensity at a point due to a charge we call source charge is defined as the force per unit charge exerted on an extremely small positive test charge when placed at that point. You can see we have defined it like this. We have taken the force and we have divided by the test charge, and of course with the condition that our test charge should be very small. So what electric field is going to tell us is not the force, but the force experienced by every coulomb or per coulomb. To make you clear, let's go back to this example here. We have the source charge, we have the test charge. Let's take the test charge to be 1 coulomb right now, which is a very wrong number, but still let's take it. Suppose I say when I kept the charge at point P, the force experienced by this 1 coulomb of charge is 10 newtons. That means I can write the force experienced per coulomb is your 10 newtons per 1 coulomb. This is what we will call as electric field at point P, or the magnitude. It simply is going to tell us how much force will be experienced by every 1 coulomb of charge when I keep at this point P due to this source charge. Now if I take the test charge from point P to your point Q, you will notice that this point charge now will not experience a force of 10 newtons, but this test charge will experience a lesser force, let's say to a value of 6 newtons. So If I write now electric field at point Q, I must write the force experienced by the test charge, which is your 6 newtons, divided by the test charge, which is your 1 coulombs. And of course, you can see when I take the test charge from point Q to R, what you expect is that the force between the test charge and the source charge will be much less, and let's say a value of around 2 newtons. So I'm going to write the electric field at point R should be equal to the 2 newtons of force experienced by the test charge due to the source charge divided by the source charge, which is your 1 coulombs, which is your 2 newtons per coulomb. The value of EP was 10 newtons per coulomb, EQ was 6 newtons per coulomb, and finally when I calculate the value of electric field at point R, we got 2 newtons per coulomb. Here you can imagine the force experience will be of course 0. So if I ask you what's the electric field at point S, you have to say it is 0. So to recap, what we have done is we have defined a quantity called electric field as the amount of force experience per unit test charge placed at that point. Now this electric field is defined at different points, and we have found the value to be different at different points. Some points corresponds to higher value of electric field, some points correspond to lower values of electric field. Now what does this number really means for us is that if I keep a charge of 1 coulomb at this point, then the force experienced by that charge must be exactly 10 newtons per coulomb applied by this charge. And because of which I can say if I keep a charge of 2 coulombs, since the 1 coulomb was experiencing a charge of 10 newtons, 2 coulomb of charge will experience a force of 20 newtons. So you can see the electric field is coming very handy for us. It's like knowing how much will be the force at this point for every 1 coulomb of charge. And obviously that number can help us to find the force on any number of coulomb of charge. And of course, if I come and take a charge of 3 coulombs and keep it here, if a 1 coulomb is going to experience a force of 10 newtons, the 3 coulombs of charge at this point should experience a force of 30 newtons. Similarly, the meaning of this EQ equals to 6 newtons per coulomb means that if I come and take a charge of 1 coulomb, keep it at this point Q, then this 1 coulomb of charge should experience a force of 6 newtons due to this charge. And of course, if I come and keep a charge of 2 coulombs at this point, this 2 coulombs of charge should experience a force of 12 newtons. So what we have learned just now is that if we have a charge which we call it source charge, this source charge will have points around it where we can find electric field due to this source charge. And you have seen the value of electric field at these points will be different. Notice there is no charge at these points, but we have fields at these points right now. If I keep 1 coulomb of charge at this point P, that 1 coulomb of charge is going to experience a force of EP. If you remember, the definition of EP was force per unit charge. Electric field at EQ means force experienced by 1 coulomb of charge is EQ. And the electric field ER at point R means force experienced by 1 coulomb of charge is ER when I keep this 1 coulomb of charge at point R. So if I ask you now, what will be the force experienced by 5 coulombs of charge when I keep at this point, your answer should be 5 times of EP. If I keep that 5 coulombs of charge at this point, the force experienced by that 5 coulombs of charge will be 5 times of EQ. And if I keep this 5 coulombs of charge at this point, the force experienced by this 5 coulombs of charge should be ER. So to wrap up, what is electric field or electric field intensity? Force experience per unit the test charge kept at that point such that the test charge is very small. The SI unit you can see of this electric field will be newtons per coulomb. And when we talk about electric field, we just need to clearly mention two things, that is your source and your point at which you are calculating the electric field. So you can see here electric field is a vector quantity because force by coulomb or by charge is vector. SI unit of electric field will be newtons per coulomb. You will see later we get another unit which will be your volt per meter. Let's look at the dimensions of your electric field. The dimensions of E must be dimension of force divided by dimensions of charge. Dimension of force, as we know, is ml t minus 2. The dimension of charge is found using this formula for your current, which is defined as charge by time. So I can write the charge as current into time, and I must write the dimension of charge must be equal to the dimension of current, which is amperes, and the dimension of time is t. In your lower classes you have seen dimensions are m, l and t for mass, length and time, and the dimension for current is your amperes. So in place of charge we have written the dimensions of AT. Now we are going to simply find the expression or the formula to calculate the electric field due to a single point charge. Here you can see I have a point charge plus Q located at a point O. I have a point called P where we are going to find the electric field, which is at a distance of R. At this point P, we are keeping a test charge which we have taken to be positive Q0, and it is very, very small. When we keep the test charge at this point P, we are now ready to calculate the force between the source charge and the test charge. On calculating the force between them, we get 1 by 4 pi epsilon naught Q times Q naught R square and some direction R naught. As this test charge will be repelled, the direction of this force will be from O towards P. Now we have defined electric field to be the amount of force experienced by the test charge per unit test charge. When we put the value of force, we are going to cancel out the test charge appearing on numerator and denominator, and we will be left out with this formula here. Now since we do not have Q0 anymore, we do not even need to use this limit. Hence we can remove this limit and we get a formula which looks like this. Here you can see we have written E equals 1 by 4 pi epsilon naught. Now you can say we have this constant here because we are calculating the electric field in air, vacuum or free space, and obviously when you come and do that in your water, we have to replace by corresponding constants. We have the source charge appearing because, if you remember, we have always talked about electric field due to a source charge. So we must have that source charge. What you can think of it is that if the source charge is large, then you are going to have a very high electric field. This R here that we have represents the distance of the charge from the point where we are calculating the electric field, and obviously this R hat or R cap represents the direction of the force experienced by that positive test charge. So if you ask me what does electric field depends upon, I'll say it depends directly on the source charge, and it depends inversely on the square of the distance of the source charge from the point. Let me show you here. If I have a charge of 1 coulomb at a point P, which is at a distance of 1 meters, we can find the electric field given by 1 by 4 pi epsilon naught. The source charge I must write and the distance from the source charge I must write. So here we have this number is 9 into 10 to the power 9. The source charge is 1 coulombs divided by distance is 1 meter, so we have 1 meter square. And when I do that, I'm simply going to get 9 into 10 to the power 9 newtons per coulomb. It simply means that if I come and keep a charge of 1 coulomb at this point P, then this 1 coulomb of charge is going to experience a force of 9 into 10 to the power 9 newtons because of this source charge that we have at point A. And again it means that if I come and put a charge of 2 coulombs, not 1 coulombs at this point P, obviously the force experienced by this 2 coulombs of charge due to this 1 coulomb of charge will be 18 into 10 to the power 19, the twice of that. Just to show you one more example here, if I have a charge of 10 coulombs as the source charge and I calculate the electric field at this point P at a distance of 1 meters, I must write 1 by 4 pi epsilon naught, the source charge which is 10 divided by the distance which is 1, so I have to square it, and of course this number you can see it is 9 into 10 to the power 9, so I'm going to get around 9 into 10 to the power 10 newtons per coulomb. So this is how you calculate your electric field at various points when the source charge is given and the distance of the source charge from that point is given. Clearly you can see when we talk about electric field is not the property of two charges, but it is the property of a single source charge. And that's why in the formula also you only have the source charge, you don't have the second charge. But if I talk about force, I must talk about both the charges.